Yeah, where is everybody? I know they're not all at APEC. There's a test. This is less important than a test? No, it's ridiculous.
All right. All right. So our first speaker today is Stanton Terry Cady. Terry did his undergrad here at the University of Illinois and graduated in 2009. And now he's working with Professor Alejandro Dominguez Garcia on distributed control.
Thanks.
Right? So when Terry's not doing research in his free time, he likes slacklining and photography and Arduinos and some other stuff. So,
Yeah. Thanks, Ming. Yeah, thanks for not reading the title too, because now I get to say this big mouthful. I've done like a lot of work in the past on distributed control for power systems. So this work is sort of diving a little bit deeper into the control side of things and not so much the power system. So you can read the title, but basically the idea is figuring out ways to increase the resiliency of distributed control and the problems that you get when you try to do that. Does this not work? Okay, there we go. Okay, so like I said, I've been doing work on distributed control, and distributed architectures have been sort of proposed as an alternative to centralized control architectures for several different applications. The one I've been working on is small footprint power systems or microgrids, and the idea is that you can, in that application, you might be deploying quickly, or the thing might be changing topology, so you want a control system that can adapt. But other applications like the coordination and cooperation of multi-vehicle systems is a big place where it's been used in lots of different broad applications. So some of the appeals of distributed control compared to centralized control is the fact that you can easily add or remove devices. So there's sort of this adaptability part of it. And it's supposed to be more resilient to individual failures. So I'm sort of talking about ways in which maybe it's not so resilient in this talk. But you don't have a centralized control like computers. So if that thing were to fail in a centralized case, then the whole system goes down, which we don't have that here. And another thing is it requires less planning to begin operation. So it sort of like has this self-assembly type advantage. And that's, like I said, good for the small footprint power systems where you might be deploying quickly without a lot of advanced planning. So like I mentioned, I want to talk about how to make distributed control more resilient. So I mentioned also that compared to the centralized control, we're eliminating a single point of failure, which is the centralized controller. But that doesn't mean that a single device or some singular part of the system could fail and cause it to collapse. So how do we get around that? So let me back up and explain ways that this distributed control actually can fail, even though we don't have the single central controller. So there can be all sorts of different failures, but the ones I'm going to focus on are communication link failures as well as local controller failures. So basically, if you have basically a minimally connected graph, so if we're doing distributed control and we're representing our communication using a graph, we kind of assume that there has to be some form of connectedness because we have to have some way for information to propagate throughout the whole system. Otherwise, we can't control it as a whole thing. So if some number of communication links fail, then obviously we're not going to have a connected system. So in the picture on the left, I've shown a network that has it's two edge connected, which means that you can get rid of any single edge and it'll still be connected. But if by chance two of them were to fail, then the system becomes disconnected and our control won't work. Similarly, a node could fail, just the device could fail itself, or it could be malicious. And again, that could break the connectedness requirement, or it could cause the system, if it's malicious, it could be trying to drive the system to some undesirable state. So just give you an example, I'll go into more details about like where these plots are coming from, but the work I've done in the past has relied on some iterative algorithms for doing distributed control. And just give you an example of what would happen if the graph were disconnected, whether it be because an edge failure or a node failure. The top graph is sort of showing how, for some control purpose, for instance, we're trying to compute the average of some initial conditions. And the average is denoted by the dashed line, but as you can see, because the graph was disconnected, not all of the nodes converge to the same value. They sort of have broken up into two different things, which is basically the two different connected components. And then again, with a malicious node, same idea if we're trying to compute the average. If you have some node that's trying to cause the system to go to some undesired state, it could set some false initial condition and drive the whole system to some ridiculous thing, which is maybe way above what the average actually is. Okay, so that's what we want to do. We want to increase resiliency to counteract these things, these edge failures and the malicious nodes or node failures. And the way I'm going to do that is two approaches. One is to use dissimilar graphs. So if you have a certain number of edges connecting your nodes, the idea is to take all of those nodes and construct separate graphs, none of which share the same edges, but remain connected. So you want to have maybe 3 different graphs, none of which share the same edge, but can be used for your distributed control purposes. The other is to use redundant controllers. So each of the local controllers actually has like 3 sub-controllers, so that if one of the sub-controllers were to become malicious or to fail, it wouldn't cause the whole system to fail. And I've tried to illustrate this here in this graph, and I kind of threw it together today, so it's not the best graphic I've put together. And it, in addition to trying to provide an idea of what I'm talking about, it also illustrates one of the problems. So in this case, I have 4 nodes, blue, yellow, red, and green. And each of them is comprised of sub-nodes A, B, and C. And the idea is that A, B, and C represent like local controllers within the node that are sort of separate. And they would each be doing their own computation for distributed control. And then at the end, they would compare their values, and that's how they would make the control decision. In addition to that, they would be using completely dissimilar edges. So you can see like I have an edge from blue A to yellow A, and then I don't have the converse, right? I don't have an edge from yellow A to blue A, or I don't reuse the blue A to yellow A. But this just illustrates how difficult it is to come up with all these different dissimilar graphs. So I couldn't actually draw the edges connecting C without reusing without reusing edges. So it's a difficult problem to solve, and actually not the one I'm going to be talking about today. So what I'm going to talk about today is more about how do you handle having 3 different local controllers, and how do you take all of their outputs and use it to make a more resilient control. Okay, so as I mentioned, it's kind of difficult to make dissimilar graphs distributively, and in fact, I couldn't figure out a way to make 3 dissimilar graphs on using undirected edges with fewer than 6 vertices. And moreover, you want to maximize the edge connectivity in each of the individual graphs. So if each of the subgraphs is sort of minimally connected, so it has one cut edge, so any edge that I remove completely disconnects it, then that's bad, because while I have redundancy, it's sort of more fragile, because anything that fails could cause it to not work properly. And what I'm going to talk about today, though, is how do you actually figure out when to have the local controllers, the redundant local controllers, compare their values. So the idea is you have 3, and at the end of this distributed computation, they compare their output, and there's a voter that sort of chooses maybe the average, or the 2 out of 3 or something like that. And you need at least 2 out of 3 to make your control decision. But the problem is these algorithms are just iterative, and so we need to know when to actually do that voting. So another thing that's sort of important is, given that the dynamic or the connectivity is going to be different among the graphs, the dynamics of these distributed algorithms is going to be a function of the connectivity, and so that's going to play a part into when they actually converge. Okay, so just to give you an example, here's another iterative, the result of an iterative algorithm where I'm trying to compute the average. This one has no failures. So rather than compute the exact average, what I'm going to suggest that we do is compute the approximate average. So if we were to iterate forever, if we were to do infinite number of iterations, we can get the exact average value. But maybe that's not so important, because if we're really using this on an application where there's an actuator making some control change, it doesn't have infinite precision, so that doesn't really make sense anyway. So why don't we find like our approximate average consensus? So rather than seek exact convergence, we're going to seek approximate convergence. So it sort of looks right here like all of the values are the same, but if you zoom in, they're not exactly. So they're very close to the same, but not exactly the same value. And what I'm going to suggest is that's good enough, and if we know the bound on that, then we can use that to decide when to vote. Okay, so just a few preliminaries on the math behind this. I mentioned earlier I'm using graph theory to represent the communication network. And in this case, I'm going to use an undirected graph denoted G. It's going to be composed of a set of vertices V and then the edges between them. So basically the unordered pair ij is in the edge set if nodes I and j can communicate. And there's the neighborhood of I, which is all the devices that node I can talk to. And then there's this notion of diameter of the graph, which is the shortest, longest path. So if you take any two nodes, the distance between them is you want to find the shortest path between them, and then the longest of all of those paths in the graph is what's called the diameter. And that's important because the algorithm that we're using converges to some epsilon that we specify times the diameter of the graph. It's a function of the diameter. Okay, so that's the graph. What we're going to be using is basically simple average consensus that relies on a linear iterative strategy. So each device is going to maintain some value, some state called x, and be denoted xi for node I. And it's going to be updated linearly according to this equation here. So it's basically just taking its value, some part of its value, and adding to it all of the portions of the values received from its neighbors. And it turns out that if we stack all of these update equations into a matrix, and we have this weight matrix called P that's comprised of all these weights, if that matrix is doubly stochastic and the graph is connected, then it turns out that they'll all converge asymptotically to some function of the initial conditions. And given the double stochasticity requirement, it turns out that'll be the average of the initial conditions. So that's, I guess, perfect average consensus or something like that, or asymptotic, where you get the exact value, but it takes forever. So there's this notion of epsilon approximate consensus, where instead of going forever, we're going to go a finite number of steps with steps which I've denoted r. And after r steps, epsilon approximate consensus after r steps, all of the node values, all the node states will be within some epsilon. So they're not the exact value, but they're all within epsilon after a finite number of state iterations. Okay, so this looks very similar to the slide before, but that was just the standard average consensus. This is I'm describing an algorithm for doing for distributed stopping, which basically is average consensus, but it has built in a mechanism for guaranteeing that you reach epsilon approximate consensus in finite time. So it's going to be the same update equation, but instead of the weights being static, they're a function of k. And again, if we stack them all up in matrix form, it sort of looks like that. And we want to have some rules so that we choose these weights p, such that this matrix is doubly stochastic, but it doesn't necessarily have to be connected. So that means that, like, I do some local rule, and if I decide not to talk to my neighbors, that's okay, so long as I preserve the double stochasticity of this matrix. And the rule that we're going to choose is basically I'll use a link if I'm within epsilon of the value received from that node. So node I will communicate with node J so long as its state is the absolute value of the difference. The absolute value of the difference between its states is bigger than epsilon. So if the value is really close, you're not going to use that edge anymore, because if you think about it, it's not really adding any information to the system because the states are already really close. You might as well not use it. And in the end, the idea is that none of the edges are in use, and everybody has converged to within epsilon times the diameter of the same value. So skipping over all the math details of that, here's a 12-node example. So you can see the graph is kind of special in the sense that it's basically two components with one edge between them, and it's sort of chosen that way because it's kind of like a worst case to show that this works. And so the initial conditions here are chosen to be this big long vector here, but it's basically just two values which are very different. A is 0.001 and B is 100. And the idea is, like I said, we want to compute the average of all these within some epsilon, where the epsilon here is 0.0001. And I'm showing here the evolution of this algorithm that I described on the previous slide. For the first 600 iterations, it turns out that it takes 950 iterations for all of the edges to be no longer in use, which means that that algorithm, the stopping criterion, has been satisfied. And I have the table down here with all the values. Without looking at all of them in detail, it's pretty clear that you can see they're all very close. I don't have the diameter of the graph, but we could look at it and see that they're all within epsilon times diameter of the average, which is 50.0005. Okay, so on to the application to like the similar graphs and the redundant controllers. So what I want to do is use that stopping algorithm to know when to vote. So in order to do that, I want to run 3 of these iterations in parallel. with different graphs. So I've chosen sort of randomly 3 different graphs, graph GA, GB, and GC, none of which share the same edges, but all of which are connected. And I'm going to run that approximate average consensus algorithm in parallel on all of them, but then after the last one stops iterating, so they're going to take different lengths of time because they have different connectivity. But after the last one stops iterating, that's when you can compare and do your voting for your control decision. So here's the evolution of the 3. You can see that the worst case is node A, or graph A here. It takes 950 iterations, whereas the graph B takes only 363. So it's kind of interesting that they vary so widely, the number of iterations that it takes. But like I said, it's definitely a function of the connectivity. And graph B here, you can sort of tell is quite a bit more connected than A and C. So this is just the sort of the standard case with no links or no edge failures. Node failures. But what I wanted to do was see what would happen if you disconnect the graph because of some edge failure. So for graph C, I basically removed this edge here between nodes 6 and 12, which makes 2 separate disconnected components, and basically simulated it to see what would happen. So again, these are exactly the same as before, which is sort of expected because it's the same graph, same initial conditions and everything. But in this case, as before, way earlier where I showed an example with disconnected graph, you can see that the 2 components sort of converge to 2 different values, and it's way off the actual average. So these top ones here converge to something like 55.5, and the bottom one is 33.3. So clearly you can see that the voter would easily be able to look at all 3 of these values and say, oh, graph C, something is wrong with that. I'm going to ignore that value, and I'm going to choose maybe one of A or B. What's really interesting, though, is that it actually takes longer, it takes less amount of fewer iterations to converge. So before I disconnected the graph, it was 673, I think, and for graph C now it's 609. So it actually takes less time. So the reason I bring that up is because I didn't expect that at first. I guess maybe because I didn't think about it that much, but it might give a way to do some diagnostics. So if you're running this for a long time and you assume the graph stays the same until you have a failure, you can maybe compare the iterations that it takes, and if it takes fewer all of a sudden, then you know some edges failed in that, something like that. So again, sort of same idea, but in this case we have a malicious node. So everything is connected again, but for graph B, I just chose node 11 to be the malicious node. So it's going to change its initial value to be several orders of magnitude what it should be to try to drive the system to some erroneous state. So these are sort of misleading because of the scale here, but clearly the middle graph converges to a way different value than the other ones. And again, it's kind of obvious that the voter could find that something is wrong with the graph B. But again, it's sort of interesting because I think this takes longer. And it actually makes sense because the convergence rate is dependent upon sort of the initial conditions. And in this case, since node 11 chose, is it node 11? Yeah, node 11 chose some initial conditions that were way higher than it should be. The sum of the initial conditions is going to change the convergence rate, so it's sort of expected to take longer. But again, that could be used for some diagnostic purposes. Okay. So as I already mentioned, it's sort of interesting how the convergence rate changes depending on if you have an edge fail or something like a node trying to perturb the system and get it to a state that it shouldn't be. Also, I found that it might be easier to make all these dissimilar graphs if you use if you rely on directed graphs. So the algorithm I described was for undirected graphs, meaning that all the communication links were bidirectional. But given that you actually have more edges to deal with in a directed setting, it might be easier to rely on that. But that means changing the algorithm because that algorithm just doesn't work for directed graphs. So some future work is developing methods for creating dissimilar graphs. And then also what I'm working on right now is doing something for distributed stop detection. So it turns out that the way that this algorithm knows when to stop, the only way that you know is sort of by having global information, which doesn't do you much good. So if you look at that weight matrix, it basically just becomes the identity matrix, and the only way to know if it's the whole system has stopped is to look at it and see if it's the identity matrix. But like I said, that's not very useful for each node to know on its own. So that's what I've been working on recently, is developing algorithms, maybe tweaks of this algorithm that allow for each of the nodes to sort of distributively know on their own using some other information that the entire network has converged within epsilon, so they know it's time to do the voting and make the change. So that's all I have. Anybody have any questions? Hal?
all the outcomes averages, as long as it's linear aspect, it's always linear convergence rate. Convergence rate is how fast the different grades like the objective or
I'm pretty sure that it does depend on the.
The number of iterations does depend on the initial condition.
Yeah. Okay.
Convergence
Sorry.
rate does not depend
Okay.
on.
Then I misspoke here. So the convergence rate is a function of the connectivity, but how long it takes to get there is a function of also the connectivity and also our initial conditions.
Yeah. So what it means is optimization convergence rate is how fast objectives decrease.
Yeah.
Either in logarithm scale or in other scale. And for convergence average is always linear. And if you don't change connectivity, it's the same convergence rate depending on second largest eigenvalue of the W major or the symmetric defect.
Right. Yeah.
So I think the observation we have for the malicious attack phase is due to the initial condition.
Yeah. So the reason is different, but like I said, it's just some ideas that I had coming out of seeing the results that maybe sort of expected from these well-known math results, but interesting way to maybe figure out what's going on in the network by like observing the iterations, the number of iterations, not how fast how long it took, but the number of iterations.
The thing is like initially you also don't know how far away all the local degrees are away from the final average, right? It's like you don't know the initial condition either by the way you reach.
That's true. Yeah. Yeah, you're right. Like I said, it was just sort of a observation, I guess, and some early ideas. But I was just thinking if you're doing basically the same thing or very similar things, maybe your initial conditions are always very similar and the final value is always very similar as well, which means that all the initial conditions are very similar. Then maybe like it's sort of just you have to leverage more information than just the number of iterations. I was just saying that it might be possible to do some diagnostics given by observing these for several rounds, like watching how it changes over time. Thanks. It's me?
So you talked about how like the time it converts depends on the connectivity, but what about like how many like it depends on how many nodes there are. That would like affect how scalable if it gets like larger.
Right. Yeah, it's the same type of thing. Like, connectivity and the number of nodes are sort of interrelated, right? So if I have a lot of nodes and they're not very well connected, then it'll take a long time.
So let's say for even amount of connectivity where like you can define it as like the number of vertices, like if you let's say quadruple the number of vertices, like sure.
Yeah, I'm not sure. Do you know how?
Yeah, so it's actually the eigenvalue of the Laplacian matrix for the graph. So it depends on the whole graph topology.
Okay.
So yeah, everything depends around the matrix.
Okay. So can't say yes or no. Someone?
I feel like a lot of people like can just have the like the maximum of the initial value like all over the graph so that like it shows how you know that how far they are.
You could actually. So there's like not that much work done in this area about distributed stopping. So this algorithm I presented was one that was presented at Allerton this year, and there's really only one other paper in the area, and it uses exactly that idea to sort of bound the iteration. So it used the max and min because you can actually find the max and min in finite time. But yeah, so I mean, I'm working with some other ideas about that, but for this it didn't need it. But that's a good idea too.
And also like in terms of the application actually is a hard because like how does this what's the information that actually
I mean, it would be like for control purposes, sort of. I mean, I'm coming at this from the application that I've worked on before, like frequency regulation, where you're measuring some frequency error and then using that to do a distributed computation to figure out how to adjust the set points of the generators. Anything else? Raj? Yeah, so if I have like an edge between node 4 and 7, one of the graphs, yeah. Yeah, I mean, so you could. I guess the idea here originally started with focusing on dissimilar graphs, and then we thought about adding redundant controllers and everything. So yeah, you're right. But it's just the idea that maybe if it's a wireless communication, maybe there's something that completely severed that communication link, right? There's some obstruction, so you don't want two communication graphs to fail just because you have like some common mode failure. Right? Or if it's a wired communication, if they run parallel to one another and both of them get cut, then yeah, yeah, you're right. No, it doesn't mess anything up. As long as you have connectivity, it doesn't matter. Another idea was to use, instead of dissimilar graphs, dissimilar mediums. So maybe have one be wired, one be wireless, two different types of wireless technologies, things like that. Okay. All right. Well, thanks.
Yeah.
All right, our second speaker today is Ololuwapo Ajala. Ololuwapo received his Bachelor of Science in 2010 from the University of Lagos in Nigeria and is currently pursuing a master's degree at the University of Illinois with Professor Sauer. His research focus includes voltage and frequency stability of microgrids.
Thank you, Saming. Today I'll be talking about power sharing for autonomous microgrids via automatic generation control. So today I'll be focusing mainly on the approach because I had some difficulty with my simulations. So let's start. So first off, I'm going to talk about distributed generation. So over here is a typical grid system with distributed generation. And over here we can see a grid connected photovoltaic system. And when the sun is up and there's enough solar irradiance, the PV generator can supply power back to the grid. And so, but there are some technical limits on the degree to which distributed generation can be implemented, because because the typical distribution system was designed for was not designed for distributed generation. So if the distributed generation systems if the distributed generation system exceeds a certain limit, it could result in frequency instability issues and voltage instability issues. And so that's one disadvantage of distributed generation. And another one is in the event that there's a contingency, such as I could thunder and we lose a line. Typically, most PV generators operate in anti-islanding mode. So when there's a loss of line, for instance, the PV generators turn off, and as we can see, experience a blackout. But the critical loads, which we tend to have uninterrupted power supplies, the UPSs will come on. So a proposed solution to this problem is the microgrid concept. And what the microgrid concept is it's an interconnection of distributed generators, distributed storage, and loads connected interconnected and connected directly to the main grid. And they have a capacity to operate in islanding mode, the autonomous mode, or grid connected mode. So over here we can see a microgrid, and typically in the event that there's a fault on the main grid, the microgrid can be isolated from the main grid, and other distributed generation can be implemented, such as wind farms, fuel cells, and as you may like. But the focus of this talk will be on the autonomous operation mode, which is when it's not grid connected. So we move over to like we know, most good things have some bad sides to them. So there are certain issues that are associated with the microgrid concept, and one of them is the protection issues, the security issues. We have load generation imbalance in the case where, for instance, we have PV generation in the microgrid, and the PV generation available doesn't match the load. Then we also have the issue of non-optimum use of renewable resources, which is in the event that which requires power sharing amongst generators. For instance, if we have like a micro turbine, if we have a micro turbine and we have PV generation interconnected together in a microgrid, how do we optimize the use of the renewable resources and minimize the use of the micro turbine so that we can minimize fuel cost? And also we have some voltage and frequency instability issues. But in this research, we focus mainly on these 4 issues. So that takes us next to the approach. So to fix the load imbalance issues, for instance, if we don't have enough PV generation, the proposed approach here is to introduce resources, generation with controllable resources. And that was the motivation behind what we looked at, which is a microgrid with a micro turbine and PV generation. But in looking at this, we realized that the mode of operation of a micro turbine and a PV generator are different because, for one, a micro turbine has inertia, which allows us to take advantage of a droop control concept, which allows equal power sharing amongst generators. But in the PV generation case, there's no inertia present. So that was a problem that was noticed. Then, so in this approach, we looked at a way to implement the droop control scheme in a PV generator. And over here, we talk a little about droop control scheme. What the droop control scheme is it's a way to share power equally, share power according to the ratings of generators. So each generator has a droop coefficient, which determines the ratio between the frequency of the generated voltage and the power output. So with the droop control, it allows when the system settles at a steady frequency, the generation from the output from each generator is shared according to the generator's rating. So over here we can see if for instance we had a 5% droop, at full load, the generation would drop, the frequency would drop by 5%. If this is no load and this is full load. And when it settles at a stable frequency, the net generation will match the load, and each generator's output will be shared according to its rating. Then we also looked at automatic generation control. Now, typically when droop control is implemented, the system settles at a frequency that's below or above 60 Hz, depending on certain factors. But automatic generation control is a centralized control method to either raise or lower the voltage to the nominal frequency of 60 hertz. So we also consider that. Um, thank you. Hopefully I can come back and like give a talk on this again when I fix my simulations. Thanks. Any questions?
So, like in distribution type of networks, the reactive power is also very important because the Rx ratio is really higher than distribution.
Yes.
So, do you think we should also include reactive power from this, like in addition to the active power control?
Yes, actually, we proposed this another Juke control scheme where we so but let me start off. You mentioned that in a distribution system that there's significant resistance, right? So from power flow, if we assume that the resistance is approximately zero, we find out that there's an inverse relationship between the real power and the frequency, and likewise between the reactive power and the voltage magnitude. But in the case of distribution systems where the resistance cannot be neglected, that's not the case. So we proposed a transformation system where okay, I don't have it here, but where we transform the powers, we transform the PQ values to we sort of create like a rotation. It's a rotation matrix that transforms the powers, the PQ values, to powers that are directly dependent on frequency. So yeah, I can talk to you about that later if you want to know more about it. So that takes me to the next phase of your question. If we can find a power relation that's inversely proportional to frequency and a power relation that's inversely proportional to voltage, then we can control voltage, magnitude, and frequency. So which allows us to use a Joule control scheme for the reactive power as well. Okay. Yeah.
I know you don't have any questions, but something one on that question. Do you take like the EQ values and multiply, you have the matrix that multiplies it, and what comes out is the vectors that where those are coupled, you can do a standard control.
Yes. Exactly. Yeah.
So you can use the both voltage and
Frequency.
I was just
Yeah.
wondering, like, if you didn't take away the voltage would go away.
If I took away the voltage,
You need a voltage controller, but you couldn't just
yeah.
ignore the voltage.
Yeah. That's why we proposed the Joule control scheme. Yeah. So
Is the transformation idea still valid, or
it,
get simulated what?
yeah, I just couldn't get it to simulate. So yeah. But
Maybe we can elaborate, but I'm just really curious about the transformation.
okay. Yeah, sure.
I'm really curious about the
Okay.
matrix looks like, how you construct it.
Yeah. So if we have like a, let's see. Um, so we got PQ, P1, Q1, P2, Q2. You can solve the power flow equations for this, and we will get um, okay. So P. Okay, like, is it possible for me to talk to you about that later? Because because it's I just thought of it. It's a long, yeah. Because okay, it's okay. It's something like this. So yeah, so it's something like this. So so it's something like this, but so it's a transformation, and we have a new P prime, Q prime, and it becomes decoupled. Yeah, something like this. I can show you later. Okay. Okay. Any more questions?
How does that? I don't know. How does the NPI thing work? Like, is it just like a little change in frequency and voltage?
Okay, I think it checks to see if there's any power coming from the main grid. So the idea behind the anti-islanding is because there's a PV generation that's supplying power to the grid. If the PV generation system, or rather, if the main grid cuts off and there's no way of knowing whether there's still PV generation, the um, the system operator could like turn back on the, maybe let's say there's a fault and the fault is fixed and there's no way of knowing whether or not the PV generation is still on or off. The system operator fixes the fault, for instance, and when the line is back on, power could be generated to the load when there's still PV generation, and which would, you could just turn out bad. So
I'm just imagine like the fault happened and the island was exactly matching. The PV exactly matched the load at the island, and if there was a fault to the rest of the grid, how would the PV generation work?
oh, okay. So typically, I think it's it measures the power from the main grid.
Uh,
Yeah.
so
So
typically you would have like a at the grid connection point.
yeah, you have like a sensor, some measurement, but yeah. Yeah, but the problem is when there's a lot of PV generation, usually there's no way of knowing whether the power that is measuring is from the main grid or from the other PV generators. So that's another problem with distributed generation system.
Power doesn't have a last name,
Oh,
whether from the grid or from the solar.
oh yeah, yeah. Yeah.
Anyway, very nice presentation.
Thank you. Thank you.